Hey guys, this is Ms. Peterson and welcome to AP Chemistry Lecture 4-1, all about net ionic equations. In this, we're going to be doing a quick review of different types of chemical reactions and how to predict products. We're going to be learning about precipitation reactions and what a precipitate is, which goes with the solubility rules, and how we write net ionic equations. You can find more information in section 4.2 of your Brown-LeMay textbook, and it corresponds to AP Chemistry topics 4.1 and 4.2. So, before we get into particular reactions, I wanted to review the 5 types of reactions that you might have learned in your general chemistry class. Okay, this categorization of chemical reactions helps because you can predict the products based on what the reactants are. That's how these are organized. For example, a synthesis reaction is when you have two small elements or small compounds coming together to form a larger compound. Okay. For example, hydrogen gas and oxygen gas coming together to form water. There's decomposition reactions in which one breaks apart into smaller ones. Common one example of this is hydrogen peroxide. We pour it on our cuts to clean it out because it produces water and oxygen gas. Single replacement reactions are reactions in which you have an element and then a compound, normally an ionic compound, and they swap partners, okay? Think about this one as there's a couple and a single person, and the single person swoops in. Double replacement is switching partners. So you have two compounds and then they just swap partners. And that's the type that we're going to be focusing on today, because those really are really common in precipitation reactions. Here's an example of one where it's not an ionic compound, but rather an acid-base reaction, which is another type of reaction that we'll be talking about this unit. There's also combustion reactions in which a hydrocarbon, compound made of just carbon and hydrogen, reacts with oxygen to produce carbon dioxide and water. Okay, now I want to emphasize that this is only one way of categorizing reactions. There's actually quite a bit of others. So let me just show you this graphic right here that I found. Okay, so when classifying our chemical reactions, you can classify them according to reactant and resultant types. That's what the list I just showed you was. You can also do it based on whether or not electrons are transferred. This is called a redox reaction that we'll be learning more about later this year. Also, if you're talking about ionic stuff and precipitation reactions, maybe you just want to classify it as, is it an ionic reaction or is it not? Or you could classify them by the energy they either produce or use. Is it an exothermic or an endothermic? So it's not that these 5 reaction types that I'm presenting here are the only way to classify reactions. Where did my OneNote go? Okay, so like I said, we'll be learning a bunch of different ways to classify reactions, and these 5 are just one way of classifying reactions that I think is useful because of its usefulness in predicting the products. Okay, so what is a precipitation reaction? Should probably start that off by showing you guys. So check out this demonstration. Okay, so let's watch a quick demonstration of a precipitation reaction. Here I have some 1 molar sodium hydroxide that I'm going to mix with my iron nitrate. And I'm going to do this reaction in this watch glass here, so hopefully we can get a nice visual of that formation of the precipitate. Okay, so there is my sodium hydroxide, and to that I'm going to be adding the iron nitrate solution. Now this is just a yellowish solution. There is no solid in here, but watch what happens when I add it to the sodium nitrate. Okay, so hopefully you guys can see this formation of a red solid. Okay, you can see those solid kind of chunks floating around in there. That is the precipitate. Now, that could either come from the sodium bonding to the nitrate or the iron bonding to the hydroxide. that's available in the solutions. Which one do you guys think it is? Okay. Well, sodium is an alkali metal, and those are always soluble. The same with nitrates. Sodium and nitrate ions love to be dissolved in solution. So this red precipitate that we are seeing here is the iron hydroxide that has formed. Okay, so all of those little specks you see are the iron nitrate. Okay, and if we let this settle for a while, we would see them sink to the bottom and not be kind of suspended in the solution. Okay, cool. Okay, so what you saw in that demonstration was iron nitrate. Okay, I'm going to go ahead and write it over here in the, actually, I'll write it down here in the big box. We had iron nitrate, which is FeNO3, it was iron 3 nitrate. That was a solution, aka aqueous, reacting with a solution of sodium hydroxide, which was also aqueous, to produce a solid. And that solid was iron hydroxide. In a little bit, we'll go over how to tell which ionic compounds are solids. And sodium nitrate, which stayed dissolved in the solution. Okay, so let me just go ahead and balance this reaction real quick. And what was going on was two solutions produced a solid product. Okay, this is called a precipitation reaction. If we could zoom in and see what was going on in the solutions, I'm going to go ahead and draw a particulate model of that for us. Okay, showing these two things coming together. So for my iron was the orange compound, so I'm going to use orange. Okay, we have the iron nitrates, the iron and the nitrate dissolved in the solution. Okay, nitrate is a polyatomic ion, so it will just stay dissolved in solution. Okay, and all of these are just separate little ions floating around in the solution. And then we also have sodium. I will use yellow for sodium. And it's hydroxide ions. Now, this isn't my best particulate diagram. I should be paying attention to sizes and things like that, but it's good enough for right now. So when these two things are mixed, okay, and it's like, pretend it's times 3. We have 3 of those atoms in there, okay? When these two things are mixed, it forms that solid precipitate. So that is the iron hydroxide. And because it's a precipitate, sometimes we'll just draw it as like a solid lump on the bottom. Okay. We could also draw it with the Fe3 plus and the hydroxide ions bonded together. Okay. But that's what's going on down here. Okay. That is our solid iron hydroxide. Okay. Meanwhile, the sodium ions are still just floating around in the solution. Okay. They're still just floating around in there. Okay. And pretend that I had more models in that other one. Same with the nitrate ions. They stayed dissolved in the solution. So meanwhile, these are still floating around, and that iron hydroxide is forming that solid. Okay, that solid is called the precipitate, an insoluble compound formed during the reaction of two soluble compounds. Okay, now these sodium ions, okay, they are still just hanging out in the solution. Same with the nitrate. They were dissolved in the solution and they're still dissolved in the solution. They're called spectator ions, okay? They're not involved in the formation of the precipitate, rather just stay dissolved in the solution the whole time. So for reactions like this, precipitation reactions, we will write things like net ionic reactions, okay? So let's go ahead and see what the net ionic reaction looks like for the reaction we just saw. So we have the molecular reaction, okay? That shows all of the compounds written together. Now, are they technically molecules? No, but for some reason we still call them the molecular reaction. Solid plus the sodium nitrate, which I don't need the parentheses because it's just a 1-to-1 ratio. Now, if we were going to write it based on what's actually going on in the solution, we would want to disassociate all of the ions that aren't stuck together as a solid because they're aqueous, they're dissolved in water. What that would look like would be, go ahead and draw it in blue here. Okay, we have iron nitrate aqueous, so that'll be Fe aqueous, and it was Fe iron 3, so Fe3 plus 3 nitrate ions, 3 NO3 minus, reacting with 3 sodium ions that are dissolved in the solution, and 3 hydroxide ions that are dissolved in the solution. But solids stay together in this type of reaction. So we have iron hydroxide, okay? It's not disassociated into solutions, so we leave it together. And then we still have the 3 sodium ions dissolved in the solution and the 3 nitrate ions. Okay, that's called the complete ionic reaction. Basically, you're just taking apart the ions that do dissolve. But you guys might notice that some things are the same on both sides of the equation. We have 3 sodiums here and 3 sodiums here. So they're not involved in the reaction. Same with the nitrates. We have 3 nitrates on both sides of the reaction. So we can cancel those out. And when we do that, what we get is our net ionic reaction. So we have Fe3 plus aqueous reacting with 3 hydroxide ions to produce the precipitate, the iron hydroxide, okay? So a net ionic reaction only shows the ones that participate or change during the reaction. So go ahead and try that summary. A molecular equation, this should say shows all of the full formulas with the molecular symbols, okay? The molecules. The complete ionic equation splits any aqueous substances into their ions, leaving non-aqueous, so the solids, liquids, and gases, intact. Where the net ionic equation crosses out the spectator ions, those ones that not involved in the reaction, leaving only the ions that participate or precipitate, you could use either of those words there, in the reaction, okay? So what ions precipitate? What ions will form this solid? Prior to this, we said, oh, if it's ionic, it dissociates. That was a lie, okay? Now we need to get in something called the solubility rules. The solubility rules are what's used to determine what ions will form insoluble or solid ionic compounds, okay? This is a table of the solubility rules. Now, an important thing to note is that the AP curriculum that says that you do not need to memorize these. However, it is going to be really helpful to know some basics and make getting through problems a lot simpler. What I do recommend that you memorize is that all compounds with an alkali metal you know, that far left-hand side of the periodic table, they're always soluble, okay? They love water. They got that one positive charge. They're always soluble. Same with nitrate, okay? Nitrates are always soluble, okay? Now, some really common insoluble ones that you're going to see over and over are silver chloride and barium sulfate, okay? And you can see those exceptions here, okay? So here, chlorine ions are always soluble, except when they're with silver, mercury, or lead, okay? Nitrate ions have no exceptions, okay? And then you'll notice for our insoluble compounds, all of the exceptions include the alkali metal cations. So we know that those are always soluble, okay? But carbonates in general are insoluble. Same with phosphates, okay? Sulfates are generally soluble except for when they have strontium, barium, mercury, or lead, okay? Now, most of the time on an AP chemistry test, they will give you the solubility rules if you need them. But it is going to be helpful to get enough practice with them that we do end up kind of memorizing the big ones. So let's practice, okay? In this table, we're going to practice predicting products and then decide which ones are soluble. So I'm going to do the first one here as an example. So silver nitrate. That's composed of a silver ion and a nitrate ion, okay? Potassium bromide is K plus and then Br minus. So when they react, this is a double replacement reaction, meaning they swap partners. So the potassium goes with the nitrate and forms potassium nitrate. It's a 1-to-1 ratio, so we're good there. Same with the silver bromide, okay? Now, let's go ahead and check and see if these ones are soluble. Well, nitrates are always soluble, so that one's going to stay dissolved. What about the bromides? Okay, let's see what it says up here. Bromines are typically soluble except for silver, mercury, and lead. And here we do have silver, so that one's going to be insoluble. Go ahead and pause this video, try the rest of the chart, and then we're going to go over it. Okay, so how'd you do? Some of these are really easy, okay? For example, potassium is an alkali metal. It's always going to be soluble. So we know all of these are soluble. Where bromine, most of them are soluble, but silver is one of the exceptions, okay? Sodium, another alkali metal. All of the compounds containing sodium are going to be soluble, but carbonate is typically insoluble. And the only exceptions are ammonium and the alkali metals, none of which are in these three, okay? Ammonium, always soluble. Hydroxide has some exceptions, like, hydroxide is typically insoluble, but the exceptions are the alkali metals, ammonium, calcium, strontium, and barium. Okay, those are the ones that are soluble. Oopsies, so that one's going to be soluble. But silver, notice, okay, silver is not an exception, so it is going to be insoluble. Okay, same with copper. Copper will be insoluble. Okay, cool. Okay, cool. Let's go ahead and do some more practice with writing these net ionic reactions. Okay, these ones we had already predicted the products for. So let's just go ahead and finish those reactions. We have KBr and AgNO3. That's these two from up here. So we said that they form KNO3, which stays dissolved in solution, and then silver bromide, which is a solid, or the precipitate. So that reaction is already balanced. When we write it out for the complete ionic, we'll have K plus and Br minus. I'm going to go ahead and leave the phase symbols out of this one just so that it doesn't get too crowded. So, and then we have Ag, plus and NO3 minus, forming K plus and NO3 minus, and then AgBr is our solid precipitate. Okay, so then we would cancel out the spectator ions to make our net ionic equation. where we have bromine ions reacting with silver ions to produce silver bromide. Okay, cool. Okay, cool. Let's try the other one, copper sulfate and sodium carbonate. So they swap partners. So now we have copper carbonate, which we had said was a solid, and sodium sulfate, which will stay dissolved in solution. Okay. So let's go ahead and balance this equation real quick. Oh, it's already balanced. Easy enough. So we can write the complete ionic. Copper 2 plus sulfate ion plus 2 sodium ions plus a carbonate ion, forming the copper carbonate, which stays together as a solid, and then the 2 sodiums and the sulfate ion. Okay, so then crossing out our spectator ions, our net ionic becomes the copper 2 plus carbonate 2 minus, forming that copper carbonate solid, copper 2 carbonate. Okay, let's go ahead and try one more, but there is a typo on this that I want you guys to fix. I actually don't want this to be sodium bicarbonate, just sodium carbonate. So replace that H with the subscript of a 2, making it sodium bicarbonate. So let me go ahead and fix that for us right now. Gonna cover up that H. And then just add that subscript of a 2. So sodium bicarbonate, which is normally a solid. Okay. So when it reacts, we will form calcium carbonate. Now, calcium carbonate, let's look at our solubility rules. Carbonate is typically insoluble, and calcium is not one of the exceptions. So it's going to form a solid. And then we have the sodium chloride, which is salt, which we do know dissolves in water. Now, this one's a little weird because we have a solid reactant, okay? So when we write our ionic, we have to keep that together as a solid, so because it is changing in the reaction. So we have the calcium and chloride ions reacting with the sodium carbonate to produce the calcium carbonate, which is the solid, and the sodium ions and the chloride ions. So note, in this reaction, there is only one spectator ion, okay? The chloride is the only ion that doesn't change in this reaction. So our net ionic will be the calcium ions plus the sodium carbonate, producing the calcium carbonate plus the 2 sodium ions. Okay, cool. Okay, cool. That's it for net ionic equations. Bye, guys.